Hey, what's up, guys? Welcome to my first video about extremal graph theory. Okay, extremal graph theory. Okay, so previous video that I just introduced this famous Erdős-Stone's theorem. So they say that the extremal NH. So this number basically means that the maximum graph, the maximum edges of the vertices graph, which does not contains the subgraph H. And if this guy divided by choose 2 and limit goes to infinity, is universal. Is universal determined by the so-called chromatic number. Basically, it's a minimum number of colors to color H. Okay, so it's here. Okay, so this is the theorem, and so this video that I'm going to talk about one special case, which this theorem doesn't cover about. So let's just write down, right? So the theorem say the following. It's basically universal determined by the chromatic number. Okay, so but this theorem doesn't tell you some special case, right? So say when chi of H is 2, so basically it means that you can use 2 color, right? You can use 2 color to color your graph. So this means that your graph is a so-called bipolar graph. Right, because you can use a 2 color to color your graph. Let's say red and blue, and there's no edges connected when 2 colors are the same. Okay. So this means that okay. So this means the following, right? This means that if limit this guy n choose to 0, right? As n goes to infinity because now chi is 2. Okay, so let's just say that your this number is basically little o of n squared, right? Because this is n choose 2, right? So it means that little o. Okay, so little o are something which is less than n squared. Oh, but this is not enough, right? Because sometimes you want to know more about this. You need to know it's less than n squared, but maybe it's n to the 1.5 or n to the 1.7 or n to the 1.8 or something. Okay. Okay, so this is the theorem that we're going to talking about. Consider the bipolar graph. Okay. So, sorry, complete bipolar graph. So let me just introduce the notation. So this is KST. Basically, this is the bipolar graph. Let's say S vertices here, and then let's say T vertices, and then there is a complete connection. So every point in S connected to every point in T. Okay, I don't want to draw it, but basically every point in S connects to every point in T. Okay, so this is a complete graph. And so we want to study the following quantity. Okay, and this quantity, right, by previous results should be less than basically it's all squared. And then what we're gonna to prove is this the C where it depends on S and T. So C is a number equal to 0 and it depends on S and T. C is a C of S and T such that this the power is basically determined by S. Let's say S is less than T. Suppose S is less than T, less or equal to T. Then this guy is basically less or equal to C times n of 2 1 minus S. Okay. Okay, and this theorem actually has a name, and let me just write down the name. Okay. What's this name? Oh, okay. So this is the theorem that we are gonna talk a proof. So this is basically due to this guy Sos-Turan theorem. Basically says the following. So the extremal number of is n of KST is less or equal to some constant C times n to 1 minus to minus 1 over S. Let's say S is less or equal to T. Okay, so the rest of the video is proving theorem. Okay, so let's go to a break. Okay, sorry. Okay, so now let's go to a proof. Okay, so the proof is simple, right? So proof basically using the double count, the counting argument. Okay, so then we want to count the number of ks1. Okay, so the number of ks1 basically means that suppose there are s points and there is some guy which is connected to all these s points. So basically this is the star shape, just 1 point and then there s point, they're all connected. So this point are connected to all s points. I want to count the number of these guy in the graph. Okay. Okay, so we want to know the upper bound and lower bound. Okay, so let's write down the definition. So how do I compute this guy? Okay, so the first calculation is very simple, right? We can just take all the vertices in the graph and consider a number of degree, right? So d of v basically is a number of points. D of v is a number of points that which v connects, and then for every d of v, you can pick s, right? You can choose s, right? So by definition, this is the number of ks1. Okay, and okay, so this is the by definition as trivial. Okay, and but this is hard to control, right? So we want to like write something like finds lower bound. Okay, so it's summary ks1 is just v choose v, d of v choose s, and we can use convexity. Okay, so the reason is that by binomial binomial coefficient is convex. Okay, so that means that we can so when the function is convex, that means that if you add it, let's say from I1 to n, then this guy is greater or equal to n times the average. Or you can prove it by your simple calculus. Okay, so it means that we want to take, so we have the summation d of v from v to all this and divide by n and choose s, and there are n here. So this is n of, so these are sum over 2 degree, sum over the degree of the vertices, which is the handshaking lemma. So it's 2n divided by n and choose s. Okay, it's simple enough. Okay, about is greater or equal to. Okay. However, we know that let's say the graph, right? This graph has no let's say the graph has no KST. Okay, so that means that we can like found the number of the lower bound. Okay, so that means that the number of ks1 must be less or equal to something, right? Must be less or equal to something because every s, so now every s vertices at most t minus 1 neighbor, right? Because if there's if there's more than t neighbor, if there's more than t minus 1 neighbor, then well there will be a graph of kst, right? So every s vertices, every s vertex at most of t minus 1 neighbor. Okay, so it means that number of this is basically less or equal to t minus 1 and n choose s, right? Because every n choose s is a s vertices, and this for every kind of this, that's at most t minus 1 place. Okay, so now what? Trivially, right? So this guy is less or equal to t minus 1 and choose s factorial. Okay. So now what we have is this kst greater or equal to something, and then this ks1 is that greater or equal to something, and then this ks1 is less or equal to something, right? So it means that this guy is greater or equal to this guy, right? Okay. So what we have is the following. All we have is the following. We have t minus 1 ns divided by x factorial greater or equal to n of 2m choose n s. Okay. Now the same thing, right? This is greater or equal to n of 2 and sorry, let's say, so asymptotics, let's consider asymptotics. So it means that n choose s is basically n s x factorial, like 1 plus small 1. Okay, so now let's say we can solve this equation, right? So this means that t minus 1 n s factorial is greater or equal to, let's say, some constant, let's say n to n divided by n, choose s factorial, like 1 plus small 1. Okay, actually there's also 1 plus small 1 here. So basically it's this. You can just, because it's original n choose s, right? So we can actually write as this: 1 plus small 1 greater or equal to n 2m divided by ns s factorial 1 plus small 1. Okay, so 2 factorial disappear. And yeah, basically so it's t minus 1 and choose s. Let's forget about this 1 plus, let's say we still read to 1, right? 1 minus small 1. And greater or equal to n of 2ms n of s. Okay, and you can see this is n of s minus 1 shifted. So 1 minus s. So it's I see. So this is n of s minus 1, right? So if you shift it to s minus 1, right? So you get 2m to the power s, that's equal to t minus 1 n of 2s minus 1 with some small constant. Okay, so now solve it. You get m that's equal to some constant c, right? Which you don't care, because it only depends on t and s and t, and n of 2 minus 1 over s plus a small 1. Okay, so let's finish this famous theorem. Okay, and so this is a theorem. Okay, but the weird thing is that we don't know, in general st, we don't know whether this is optimal. Okay, so actually these guys in general is not sure about it's optimal or not, right? So this is still an open question. So see you guys next videos.